First of all, I should thanks to the organizers for giving me a chance to give a talk. And my title is Towers in Toric Topology. And this is joint work with Jong Baek-sung and my advisor, Dong Yeop-seo. My talk consists of two parts. First, I will explain what towers we would like to consider bath tower and generalized bath towers and a kind of new notion, flag bath towers. And second, on the second part, I will explain generalized bath tower and associated flag bath towers. So, okay. I will start with the definition of bath towers. This is first introduced by Grossberg and Carson. Carson in 1994. Bath tower is an iterated sequence of CP1 bundles. It means that first start a point. This is the zero stage of bath tower. This is let's say M0, and consider CP1 over there. This is M1, and then taking a trivial line bundle C and plus a complex line bundle. Let me denote it by L2, and then consider the induced projective bundle of this sum of two line bundles. And we call it M2, and this is actually the two-stage bath tower. And then you can do the same thing up to M. Let's say P, here I have M minus 1, and then you take trivial line bundle and some complex line bundle on there, and then you take consider the induced projective bundle LM and denote it by MM, and we call those MM by M stage both manifold. And then there are several examples. As you can see, CP1 is always a bath tower. This is one of the trivial examples. And also, Hilbert surfaces are also bath tower. Surfaces. And as you might know, both of them are smooth, compact smooth toric varieties, and these M-stage bath manifolds are always compact smooth toric varieties. Is that M's are smooth, compact toric projective toric varieties, and also whose orbit space can be understood as cube, m-dimensional cube. I will denote it by just m times of the closed interval. And actually, I just want to mention that in their paper, they consider bath tower because of this reason. Some bath manifolds are diffeomorphic to Bath-Samuelson varieties, Bath-Samuelson manifolds. And those Bas-Samuelson manifolds plays an important role in representation theory. Those manifolds are important in representation theory. And by using this diffeomorphism, they shows that some of the, some moment map image of those band manifolds encode some representation theoretic information. So that is the first definition. And then in 2008, Professor Masuda and Professor Seo introduced a kind of generalization, extended notion of Bat tower. The name of it is Generalized Bat tower. Generalized Bat tower. Okay, and instead of taking the sum of two line bundles, you can take any sum of line bundles. So it means that generalized Bat tower is an iterative sequence of CP and NJ bundles. And this is Masuda. So, as same as Bat tower, you are starting a point, and then consider CPN1. Then this is the first stage of generalized Bat tower, and then you take first trivial line bundle and sum of L21 plus L2 and 2. So you are taking N2 plus 1, sum of N2 plus 1 line bundles. And then you are consider the induced projective space. Then L21 plus L2 and 2. And this is N2. And this is two-stage generalized Bat tower. And if you do the same thing, then you will get here N minus 1, and you will take trivial line bundle and with some LM1 plus LM2 plus LM and M, and then considering its induced projective bundle, then you have this LM and M, and this is the definition of NM. So we call NM by M stage generalized both manifold. And then as you can see, CPNs for ON, CPNs are the trivial example of generalized band manifolds. And also, if you consider just sum of two line bundles, then you can see that all of the band manifolds are the generalized band manifold. What I mean here, both manifold. And also, those M-stage generalized band manifold is also a smooth, compact projective toric varieties, and whose orbit space is the product of simplices. Delta N1 times delta N2 times delta N. Actually, we have been trying to find some the similar things on the representation theory, but it is very hard to find the similar things. So we extend the notion of generalized Bat tower as by taking, instead of taking projective bundle, but taking a flag, induced flag bundle. I will explain about it. So this is our definition of flagged but tower. 신타로 쿠로키, me and Professor Sa. So flagged. A flag but tower is an iterative sequence of flag bundles. Flag nj plus 1 bundles. What I mean that first, F0 is always a point, and then we are consider the flag manifold. Flag n1 plus 1 and denoted by f1. This is the full flag in C n1 plus 1. So I would like to recall the definition of this full flag. Flag n1 plus 1 is the set of those vector spaces v1, v2, vn1 inside of C of n1 plus 1, and all of those whose complex dimension of vi is always equal to I, or I. This is the set of complete flag. And then consider the line bundles on there. And first taking a trivial line bundle and plus some n2 number of line bundles on there, and then consider the induced flag bundle over there. This gives us some new manifolds over the flag manifold. We call it F2. And here, what is the induced bundle? I would like to recall the definition of induced bundle. It means that if we have vector bundle, vector bundle E over X, this is vector bundle. Then induced flag bundle E is this is the fiber bundle whose fiber is flag spaces. What I mean that for every point P in X, the fiber of this bundle is nothing but a flag of the fiber of original vector bundle. If we consider, this EP means the fiber of the vector bundle on the point P, and then by taking complete flag, then this is the fiber of this induced flag bundle. So it means that on each point, it has each fiber consists of flags. So this is the definition of induced flag bundle. This is F2, and when you do the same thing up to there, then you have here you have F n minus 1, and consider an m plus 1 of line bundles, complex line bundles, and taking flag, then you will get Fm. And as you can see, all of them has the fibers as complete flags. Here you have flag, your fiber is flag n2 plus 1, and here you have your fiber is flag nm plus 1. So we call Fm M stage flagged but manifold. This is our definition, flag but manifold, and there are some examples like CP flag n plus 1, is always the flagged bond manifold. And also, as you can see, if you consider just sum of two line bundles, then if you consider taking the full flag on there, then it is exactly the same as the projective bundle, induced projective bundle. So it means that bond manifolds are always flagged bond manifold. So yeah, I have two kind of examples. Yes, and unfortunately, these M-stage flagged bond manifolds are not a toric manifold, but it has the very nice torus sections. What I mean that Fm on Fm it has C complex torus of dimension n1 plus n2 plus and M, this dimensional complex torus acting on Fm. And also by using under this section, this manifold is GKM manifold. It means that it has very nice torus action on there. So yeah, I would like to summary all of those three kind of towers. First, if you have but manifold, I want to denote it by just Bm. M-stage bond manifold is complex M-dimensional manifold which has the same dimensional complex torus action, and also this is GKM. This is toric manifold, and also generalized bond manifold is whose complex dimension is n1 plus nm, and there is complex, the same dimensional complex torus acting on this, and flagged bond manifold, and also this is toric, and flagged bond manifold has of n1 times n1 plus 1 and m times nm plus 1. This is complex of this dimensional complex manifold, and it has the complex torus section of dimension this. And as I mentioned before, bond manifolds, the set of bond manifolds is contained in the set of generalized bond manifolds, and also this is contained in flagged bond manifold, and you can draw the picture Venn diagram like this. This is generalized. Here I would like to put flagged bond manifolds and generalized bond manifold, and you have bond manifolds on there. And I want to remark that, as I mentioned before, some of bond manifolds are diffeomorphic to Bose-Samuelson manifolds, so that by using the geometry of bond manifolds, we can read the representation theory. And recently we showed that some part of those flagged bond manifolds also encode some representation theoretic meaning. What I mean that there, I would like to draw a picture like this. This is diffeomorphism, and somehow this is Bose-Samuelson manifolds, and we extend the notion of Bose-Samuelson manifolds, and we call it flagged Bose-Samuelson manifolds. And by using this diffeomorphism, we are expecting that we can read some representation theory by using this flagged bond manifold. So, yeah, this is diffeomorphism class of them.
Why don't you allow partial flags so that the
diagram? Yeah, you're right. I recently I just recognized that. Yeah, you're exact. Yeah, if we allowed partial flag, then this is really the generalized notion of this generalized bond manifold. Yeah.
But this,
yeah, you're right.
basically,
this disk.
Is everything a projective variety?
Yes, I think so.
Another question is why you restrict. So you are giving up being toric variety, right?
This?
Then
Yeah, we are giving up.
Restrict your bundles to be
Full flag?
bundles.
Line bundles. So action, yeah, action.
Yeah, in order to get more action.
More action.
So the maximum action. Maximum force. But we don't have to consider this. So this is A type. Very big type.
Okay, then I would like to move part 2. First, I would like to remark that for a given any vector bundle on the manifold, this is vector bundle, we don't need to assume that it can be expressed as the sum of line bundles, but for every vector bundle, if you consider its induced flag bundle on there, and if you consider induced projective bundle, then you can always find the bundle map from here to there, which is surjective. Yeah, to be more precisely, as I mentioned before, at each point, its fiber consists of the full flag. So I will denote it by V1, V2, let's say EP. And then this maps to just V1. And this kind of map gives you the bundle map from this induced flag bundle to induced project bundle. So by using this kind of observation, we can define associated flag bar tower as follows. So let's say I have N0 and 1. This is the generalized bar tower, and 2 and M generalized bar tower. And then I want to denote the actually when you make this first stage generalized bar tower, we just take the vector space, and I will denote it by KAIST1. And for convenience, I would like to denote the sum of line bundles over this first stage but generalized bar manifold as just KAIST2. This is sum of line bundles on N1, and then we have KAIST3, and M. And I have actually both of them are just points, so they are exactly the same. This is 0 stage of my associated flag bar tower, and then I will take induced flag of KAIST1. This is just the full flag manifold. And then, as I mentioned before, we can always find the map from the full flag to this project space. This is just project space, and I will denote it by Q1. And then you can pulling back this KAIST2 through this Q1. So Q1 pullback of KAIST2. And then this is also the sum of line bundles over the flag manifold. And then you will consider the induced flag bundle of this sum of line bundles. And this is our second stage of associated flagified bar tower. And then you need to find the map from here to there, but it is a little bit tricky. So let's say here, I will explain what is the map Q2. What is Q2? This map is that I have flag C1 and N1. This is Q1. And then I have line bundle C2. And consider, and this is pulling back of C2. And then taking induced flag bundle of both of some line bundles. What I mean, consider Q1 pull back C2, and here consider induced flag bundle of C2. Then naturally you can have the map from here to there, and then again you have induced projective bundle of C2, and there is the surjective map from here to there. So by composing those two maps, you can get the map Q2 from this two-stage flagged band manifold to two-stage generalized band manifold. This is Q2. And then by using this Q2, you can also put back C3 to here. And then by the same way, you can define associate for a given generalized bar tower, you can always find the associated flagged bar tower. This tower we call associated flagified bar tower. Yeah. When we find this kind of relation, we want to know what it is and what can we say about those relationships. But last May, when we visit Japan, Tatsuya and Hiraku teaches us the following result about the flag manifold and the projective space. This is theorem by it is very hard to pronounce his name, but yeah, I'm sorry. Kiriachiko, yeah, Kiriachiko. Yeah. Anyway, he proves that, as you know, n-dimensional complex torus always has the action on this n+1 full flag. And then there exists a point x in this flag n+1 such that if you consider the torus orbit of this point and taking a closure, then it is, by definition, it is a toric variety inside in this flag. I will denote it by C star n dot x in. This is the permutahedral variety. Yeah, I will explain what it is. It's the permutahedral variety. And then actually this can be understood. This is the toric variety whose underlying polytope is permutahedron, and it can be also understood by this is smooth, the smooth, compact, and projective toric variety, which can be obtained by blowing up all the torus invariant subspaces of CPN. Actually, the name of this variety, somebody this permutohedral variety called as complex toric variety associated to the root system type A, and somebody, and this also can be understood as a regular semi-simple Hessenberg variety. Anyway, this is the permutohedral variety. And then what does it mean? So for example, if you consider the simplex CP2 with this triangle, and if you consider the characteristic vectors as -1, 0, and 0, -1, and 1, 1, and then, as you know, all of those faces corresponds to torus invariant subspaces of CPN. So blowing up all of the torus invariant subspaces means that here for this example, we are taking the face cutting near those 3 fixed points, and then after then, actually the remaining faces are just facets. So if you consider the face cut, then it is same as the original polytope. So this polytope, as you can see, this is the permutahedron of dimension 2. I will denote it by pi 2. And then this is the variety with this polytope and whose characteristic, whose vectors given by the sum of those vectors. And then for the case of one more, for 3-dimensional case, you can put the simplex on this positive quadrant of R3, and then first you take the blowing up of near the fixed point, and you will get those. What was it? And then consider the face cut of the edges, then you will get permutahedron. I'm sorry. I think it is too small. Anyway, if you cut all of faces, then you will get the permutahedron. So actually, this is the permutahedral variety. And then our main result is that let's say and if you have generalized Bott tower, and then let Fm be an associated flat Bott tower, then as I mentioned before, it has the torus section, complex torus of dimension n1 plus and m, and the complex torus of dimension, the same dimensional complex torus act on both spaces. And then our main theorem says that there exists a point x in Fm such that if you consider the torus orbit closure of this point, C star of n1 and m dot x, and this is the toric variety inside of our associated flagged Bott tower, then this is the smooth compact projective toric variety obtained by, this is toric variety obtained by blowing up some, not all, but some, blowing up the appropriate torus invariant subspaces of this generalized bar tower. So I would like to show you an example. And actually this is the toric variety whose polytope is the permutahedral variety n1 times permutahedral variety n2 times permutahedral variety nm. This is the toric variety whose underlying polytope is this, the product of permutahedron. Then, for example, I think this is the most easiest example that I can show you. So this is the polytope of generalized bar tower, this is two-stage generalized bar tower, and 2, and let me take just product of projective spaces. This is trivial bundle. Trivial. And this is just prism. And then if you consider the face cut of those 3 edges, vertical edges, then you will get this polytope. Hexagon times interval. And this is the toric variety inside of our flagified bar tower, associated flagified bar tower. And this is actually flag 3 times flag 2 times flag 1. I'm sorry, flag 3 times flag 2. Yeah, I'm sorry. Yeah. And similarly, yeah, we can get those kind of result. And there are some further works we want to do. Actually, we have been compute the torus orbit closure inside it of associated flagified bar tower. So what I mean that if you consider the generalized bar tower, and this is the set of flagified bar tower, and if you choose generalized bar tower, then you can get a associated flagified bar tower, but the map of this, the image of this map is the proper set. So we have been computed the torus orbit closures of those proper set of flagified bar tower, but we don't know the torus orbit closure of flagified bar tower, which is not an associated flagified bar tower. So for a flagified bar tower, which might not be an associated flagified bar tower, what is? Can we obtain the similar result? What I mean here, similar is, I don't know, what it is, but can we describe the toric variety inside of flagged bath tower? So, yeah, I will stop here.